All right, let's get right into it. Deep down, at the very core of your computer, there's a constant conversation happening. Your apps, running out in what we call user space, need to talk to the brain of the operation, the Linux kernel. But how do they do that? It's one of the most fundamental things in all of computing, and today we're going to pull back the curtain on two very different ways this conversation happens. The classic old-school I/O control and the modern, super flexible system called Netlink.
I mean, have you ever really stopped to think about it? When you plug in a flash drive, or you change your display settings, or you fire up a tool to check your system's performance, your application is sending a request deep, deep into the kernel. This isn't just some simple function call. It's a carefully managed dialogue with the most powerful, most protected part of the entire operating system. So here's the best way to think about it. The kernel is like a super secure bank vault. It's guarding all the important stuff. The hardware, the system resources. An app can't just barge in and start messing around. Nope. It needs a formal, secure way to ask for permission. And ioctl and Netlink, well, they are the gatekeepers. They are two totally different ways to ask for the keys to that vault.
So let's start with the original, the workhorse that's been around for, well, forever, ioctl, which, by the way, stands for Input-Output Control.
According to the kernel's own documentation, this is the most common way for an app to talk to a device driver. So what is it really? It's a direct system call. And that's the official formal way an application asks the kernel, hey, can you please do this privileged task for me that I can't do myself? It's a single, powerful command that lets an app give very, very specific instructions to a piece of hardware, whether it's your graphics card, a hard drive, you name it.
This slide really gets to the heart of what I/O control is all about. First, it's direct. It's a straight shot, a dedicated phone line from your app to a specific driver. No middleman. This directness makes it incredibly powerful. You get this really fine-grained, low-level control over hardware. And because of that, it's ubiquitous. I mean, it is everywhere inside the kernel. It's a fundamental piece of how Linux works.
But, and you knew there was a but coming, right? That power and directness, it comes with a pretty big price tag. ioctl has a reputation for being, well, rigid. And sometimes that rigidity can be a little dangerous to maintain over time.
And hey, don't just take my word for it. This is a quote straight from the kernel's own documentation. The developers themselves are warning you. They're saying, look, once you create an ioctl command, changing it later is incredibly hard, without just breaking things, without causing this huge domino effect that messes up all the apps that rely on it. And for long-term stability, that's a huge problem.
So why? Why is it so brittle? Well, it's because the app and the driver have this super strict contract. Think of it like a paper form with exactly 2 boxes on it. The driver is expecting that exact form. Now, what happens if a kernel developer decides to add a 3rd box to the form? Well, an older app that doesn't know about the new box is going to send the old 2-box form. The driver gets the wrong size, gets confused, misreads the data, and boom, you could be looking at a system crash.
And this exact problem, this rigidity, is precisely why Netlink was created. It's a completely different philosophy, a more modern, flexible way for the kernel to have these conversations.
This right here nails the fundamental difference. Where ioctl is that direct, one-and-done system call, Netlink is totally different. It works more like a network connection, but one that lives entirely inside your operating system. It uses something called a socket to create this flexible, ongoing channel for communication.
At its heart, Netlink is really the replacement for ioctl that we needed for the modern world. By using that socket-based model, it just opens up a whole new world of possibilities for how apps and the kernel can talk to each other, getting us away from that fragile, fixed structure approach.
And oh man, those possibilities bring some huge advantages. First up, flexibility. Remember I/O control's rigid paper form? Well, Netlink messages are more like a collection of labeled envelopes. Every piece of data has a tag on it. So, if a new version of the kernel wants to add a new piece of data, a new envelope, older apps just see a label they don't recognize and they just ignore it. No breakage. Second, it's asynchronous. The kernel can act like a radio tower. It can broadcast messages out to lots of apps at once, yelling, "Hey everyone, a new USB drive was just plugged in," to any app that's tuned in. And finally, it's standardized, which just makes the whole system cleaner and way easier to work with.
Okay, so with all these amazing advantages, you're probably thinking, Netlink must have completely replaced ioctl by now, right? Well, as is usually the case, the reality is a little more nuanced than that.
This table is really the key takeaway for this whole thing. Look, for simple, direct hardware commands where the interface isn't going to change, ioctl is still a perfectly good, really efficient choice. Think of it like a scalpel, perfect for one specific job. But for complex stuff, like setting up network interfaces or firewall rules, or for anything that needs to evolve over time and send out those asynchronous alerts, Netlink is the clear winner. It's the versatile Swiss Army knife.
In fact, kernel developers have actually tried to replace ioctl with Netlink in some areas and found that, in their own words, it was inadequate. They realized that Netlink's main job is to be a message bus, not a drop-in replacement for every single thing ioctl does. Sometimes you just need that simple, direct system call. So no, ioctl is not obsolete. It's a specialized tool that still has a really important job to do.
And all of this brings us to one last really interesting question. The jump from ioctl to Netlink proves that as our systems get more and more complex, the actual language we use to control them has to evolve too. So what's next? As we head towards even more dynamic, more distributed systems, are we going to need a whole new way to have that crucial conversation with the kernel? It's definitely something to think about.